I'm going to talk to you about the ideal gas law. The ideal gas law relates the amount of a substance, in other words, the mole, to pressure, volume, and temperature. Now, at the end of the last video, we derived an expression for the ideal gas law. This derivation was the culmination of combining Boyle's law, Charles's law, Gay-Lussac's law, and Avogadro's law into one equation. Now, the ideal gas law constant is explicitly represented with a capital R. So if we take what we derived in the last video and we substitute a capital R for the K, we get the gas law constant expressed in terms of the ideal gas law. So the ideal gas law states that pressure multiplied by volume is equal to the number of moles represented with a lowercase n multiplied by the ideal gas law constant, capital R, multiplied by temperature in Kelvin. Now, what we're going to do is actually calculate R. We're going to calculate the ideal gas law constant. I want you to understand where this value comes from. It comes from the standard temperature and pressure conditions for a gas. So let's go ahead and plug in conditions for STP. We know that we have 1 atmosphere of pressure, and we know that the standard temperature is 0 degrees Celsius, and when we add that to 273 Kelvin, we get 273 Kelvin. We're going to calculate R for 1 mole. So the question is, what is our volume? Well, recall from Avogadro's hypothesis and our studies of molar volume that any gas at STP will occupy 22.4 liters of volume. So we are now going to use this information to calculate the ideal gas law constant, R. Let's go ahead and write down what we know. We know the pressure, we know the volume, we know the amount of the substance, we know the temperature. So all we need to do is algebraically rearrange this to solve for R. When we do this, we get a value of R of 0.0821, and our units would be atmospheres times liters divided by moles times Kelvin. So those are the units for the ideal gas law constant, R. Again, in this particular portion of the video, I am showing you where the value for the ideal gas law comes from. You now know it is calculated using the conditions of a gas at standard temperature and pressure for 1 mole. The ideal gas law continues off of several assumptions made for kinetic molecular theory. Namely, I want to accentuate 2 of these assumptions. Number 1, gas molecules have 0 volume when compared to the space between them. In other words, these molecules are so small relative to the space between them that we can consider their volume to be negligible, and indeed, in this case, 0. Number 2, gas molecules have no attractive and repulsive forces. So there are no intermolecular forces occurring among these molecules. These are 2 out of the 5 assumptions we detailed in kinetic molecular theory, and these 2 are very important for understanding how the ideal gas law works and why, in most conditions, the ideal gas law is accurate. So we can see in this animation, we have a given amount or of these gaseous particles, and they are moving, exhibiting basically a straight line motion. They are essentially point masses. Any collisions that are occurring are completely elastic, which means kinetic energy is conserved. And again, these molecules are not attracted or repelled from one another. So let's look at our equation for the ideal gas law. And let's rearrange it and look at volume. So for assumptions 1 and 2 to be valid, let's think of a vessel with a very large volume. Think about it. If there's a large volume, then sure, the volume of the individual particles would be negligible compared to the volume between them. Also, if there was a very large volume at a given kinetic energy, in other words, at a given temperature, then we would expect the attractive and repulsive forces between molecules to also be negligible because they are so far apart in this large volume. If we look now from a mathematical perspective at what would result in a large volume, we can see that the number of moles is constant, the ideal gas law is constant. What happens if temperature goes down? Well, if temperature goes down, then volume goes down. All right. If volume goes down, then these moles of gaseous particles are going to be closer to one another. So their volume that they occupy is no longer negligible. The intermolecular forces among them is more pronounced because they're in such close proximity. That would be at extremely low temperatures. Now let's look at the other variable here, pressure. As pressure increases, the volume decreases, all right? That's Boyle's law. They're inversely proportional to one another. So if the volume is small, in other words, if there's a tremendous amount of pressure, then these molecules, they're moving faster and they're in a smaller volume. If they're in a smaller volume, then they're going to interact with one another. Again, this would nullify assumptions 1 and 2. So to go ahead and get this defined in your books, as long as the temperature is not too low and the pressure is not too high, gases behave ideally. And under most conditions, gases behave ideally. Now, there are equations and ways that we can represent and calculate based on ratios between an ideal gas and a non-ideal gas, but that is beyond the scope of what we're trying to look at in this video and in this course. So what is very important for you to see, if the temperature is too low or if the pressure is too high, mathematically, both of those are going to decrease the volume. And if volume is decreased, then assumptions 1 and 2 are no longer valid because there would be intermolecular forces among molecules. The molecules would occupy a volume that we could not ignore. All right, so let's go ahead and do one ideal gas law problem. All right, this is the first time where we've been able to look at all of these variables in concert. So we have a 1.45 liter container. It's filled with sulfur dioxide gas at a pressure of 115 kilopascals and a temperature of 28 degrees Celsius. Part 1. How many moles of sulfur dioxide are there in the container? All right, so this means, given these variables, we're going to utilize the ideal gas law. So let's write down our variables, and let's go ahead and put what we know and what we're trying to find. Well, we're trying to find the number, or excuse me, the amount of the substance, the amount of moles. We're given all the other values, and of course, at the beginning of this video, we calculated the value for the ideal gas law from an expression that we derived in gases 4. Now, one thing that I need to make sure I accentuate is when using the ideal gas law, you will need to use atmospheres as your unit for pressure, liters for volume, Kelvin for temperature, obviously moles for mole, and the units for the ideal gas law. So we need to do a conversion here. Let's go ahead and convert 115 kilopascals into atmospheres here. So using a little dimensional analysis, we're able to do that. And we have our new value of 1.135 atmospheres. Let's use the equation and go ahead and plug in our numbers for each variable. Let's rearrange for N, which is the amount of moles, and mathematically solve this problem to be the amount of moles of sulfur dioxide is equal to 0.067 moles. Now, part 2, calculate the mass of sulfur dioxide in the container. Well, now that we know the number of moles, we can simply use molar mass from the periodic table to convert this into mass of sulfur dioxide. So using dimensional analysis and the fact that there are 64.06 grams of sulfur dioxide in 1 mole of sulfur dioxide, we can solve part 2 and say there are 4.29 grams of sulfur dioxide, and that's with 3 significant digits. As we continue to explore our Georgia Standards of Excellence, we have once again shown how we can put together the properties that affect gases such as volume, temperature, pressure, and moles. I'll see you guys in class.